Please join me in welcoming our first Mosquito Mapper presentation about predicting NDVI values from globe land cover RGB measurements with multiple linear regression.
Hey guys, my name is Prachi Ingle and I'm a current high school senior. Last summer, I participated in the NASA 2020 SEEDS Mosquito Habitat Mapper internship, where we learned about mosquito and land cover tracking tools. Through this internship, I worked with a smaller group to investigate whether we could use Globe Observer land cover photos to predict satellite measurements of vegetation. Before we start, I would like to thank our project mentors, Rusty, Peter, and Cassie, for introducing us to in-situ and satellite data collection techniques and for guiding us through the scientific process. I would also like to thank the SEEDS program coordinators, Selena Miller, Marco Baggio, and Teresa Sherwin. Today, I'm excited to present our group Summer SEEDS research project. We used machine learning to predict normalized difference vegetation indices from globe land cover images. First, I'd like to share the background of our project. Millions of individuals around the world die of mosquito-borne diseases like malaria, dengue, and West Nile. Understanding mosquito population dynamics can help us develop better public health interventions to reduce the transmission of these diseases. Since mosquito breeding activity is heavily associated with ecology, we have to understand how vegetation influences their populations. To establish this link, it's important for us to accurately measure vegetation across the globe. Vegetation is a tricky variable to measure. Currently, researchers use the Terra Modis satellite to capture the NDVI, or Normalized Difference Vegetation Index. However, these satellite measurements of NDVI are often confounded by clouds, shadows, and landscape changes. This is where citizen science comes in. People can contribute photographs of their local landscapes. If we link these photographs to the satellite measurements, we can start filling in the gaps. So in our project, we quantitatively linked citizen-collected photographs to the satellite NDVI measurements. Our work ultimately will help us construct more accurate representations of vegetative cover in different areas around the world. Now I'll share more details about the goals of our project. Over the past decade, citizen science engagement has skyrocketed. Through tools like the Globe Observer app, citizens can conduct guided observations of mosquito presence and land cover features. In our study, we use citizen-collected images. We extract their RGB, meaning red, green, and blue, quantities to estimate the NDVI. Our project not only numerically summarizes globe land cover images through the RGB values, but also explores connections between the citizen ground images and the satellite measurements. Here is our approach. The independent variables for our model are the RGB values from each Globe Observer image. We first took land cover images from the Globe database as a CSV, implementing pre-processing procedures to remove any extraneous observations and focus on contributions from fellow 2020 SEEDS interns. From the Globe image URLs, we created an algorithm to fetch the image, compress it to a thumbnail, and extract the RGB values from each thumbnail pixel. Then, the image, we created a color vector of each image's median RG and B values. The table on the bottom right shows our calculated median RGB for our first few observations. Our model predicts NDVI values. To get this dependent variable, we use the Satellite Appears Query database to get the NDVIs for each globe study site. We generated a unique ID for each observation and used their latitude and longitude to tie the NDVI to the RGB median values. The table on the right shows the cleaned up version of the NDVIs given per location. Since satellites measure NDVI over a range of dates, we had to take the median NDVI of all non-extraneous values per location. Using Python, we then combine each observation's RGB median color vector with its respective NDVI measurement in a separate data frame. We then perform multiple linear regression analysis using scikit machine learning packages. So we got a formula in the general format of predicted NDVI is equal to our intercept, meaning the noise of our model, plus the coefficients times the RGB variables, where R, G, and B each have a linear relationship with the predicted NDVI. Here are our results. We trained our model on a random sample of our data set. This data included a location's recorded RGB values and the measured NDVI. On this slide, I have shared a multiple linear regression model that we were able to construct. This formula makes sense given there's a positive relationship between the green coefficient and the vegetation index. However, there is some room for improvement. The y-intercept indicates that we have moderate noise in our prediction, which has implications I'll go over in a moment. We then tested our model on the rest of our data set. The table below displays some of our NDVI predictions from the median RGB values. Here is a scatter plot of our actual and our predicted NDVI values at the test locations. The orange stars represent our predictions, while the blue dots represent like the actual NDVIs for that observation. As you can see, the predicted values are less spread out than the actual values, indicating while our model follows the general trend, it fails to capture the true variability of the NDVI distribution. We quantified our error using the root mean squared error, which is basically like the typical distance between our true and predicted NDVI. Since this was less than our standard deviation, we can say that our model performed reasonably well in predicting the NDVI. However, there is room for improvement. But what does this actually mean? Let's visualize our predictions a bit further. Here's an example of a good prediction. In the left photograph, we see fairly consistent vegetative ground cover without any majorly disruptive features like human development. Also, the camera is like properly angled to capture a good summary of the area's land cover features. In the aerial view on the right, we see that the picture's location, represented by the red diamond, matches the location where the photographer that was recorded in the globe database, which is the blue marker. This means that the photograph accurately portrays the area captured by the satellite, increasing the accuracy of our prediction. Here's an example of a mediocre prediction. Looking at the left photo, while a large area of grass appears to surround the photographer, the photo also has cars, a road, and a sign. This human development differs from the grass where the person's actually standing, resulting in a lower predicted NDVI than the actual NDVI for that location. Also, if we look at the satellite's perspective to the right, it appears that the image's location, the red diamond, does not match the globe location, the blue marker. In this case, the discrepancy does not really affect our prediction, since the ground cover of both the red diamond and the blue marker are fairly similar. However, this could explain some of our error. Here's an example of a poor prediction. Because of the water's reflection, the photograph on the left looks very green, despite the very small amount of vegetation. Also, Globe recorded this person's location to be at the blue marker, which is really far from the actual photograph site, which is the red diamond. So while the model sees green and assumes higher vegetation, the Terramoda satellite sees an impervious surface where the photographer is actually standing and measures lower vegetation. To extend our models further, we could include other variables like image texture, vegetation types, or mosquito levels. We could also test other non-linear mathematical models and compare their predictive performance against our current model. To close, we just wanted to offer some insight into our experience as research interns from the SEEDS program. We really appreciate the opportunity to learn from NASA mentors and collaborate with other students and scientists. Although because of COVID, we were unable to conduct significant fieldwork this summer, we learned many other important skills like how to conduct research virtually. Overall, SEEDS has been an absolutely amazing program and an incredible learning opportunity. Through this program, my group members and I grew even more excited about STEM research. We were amazed by the sheer potential of citizen science and accelerating ecological research. Personally, I realized my love for scientific computing, and in the future, I'd love to continue working with satellite data to create similar yet more robust predictive models. Thank you all for attending our presentation.
Great job.
So if anyone has a question for Prachi, would you put it in the chat box? What do you feel is your biggest challenge, or was your biggest challenge in conducting your research?
I think it was mostly just like understanding the data sets and understanding like what we could use and what was not usable. We particularly focused on observations made by 2020 STEM interns. So that data cleanup process was very time consuming in terms of like isolating who exactly we wanted and choosing observations that actually had land cover photos with it.
Well, congratulations on doing such an excellent job with your research. I know that we all learned a lot. We have one other team from the Mosquito Mapper group. And so we will, we have one more question for Prachi. What career path did this experience open you up to?
I think I was already somewhat interested in computer science, but I didn't know what I wanted to use it for. Through this opportunity, I realized just how powerful computer science was in solving like real world problems. And I've always been really interested in the environment, especially because I live in Texas. So we're starting to see the effects of climate change on our area, from more mosquito incidences to more extreme weather. So then the fact that I can somehow combine computer science to investigate environmental phenomena is a really exciting avenue that I hope to continue to pursue.